A small pebble dropped in a pool of still water creates ripples on the surface. These ripples form concentric circular rings around the source of disturbance and spread outward along the surface. When these ripples reach a point on the surface of water, the point starts oscillating up and down. Different points, which are at the same distance from the source of the disturbance, oscillate in phase. That means all these points reach the crest or trough at the same time. The locus of all such points having the same phase of oscillation is called a wave front. In case of water waves on the surface of water, we observe circular wave fronts. Each circular wave front is a locus of all points having the same phase of oscillation. The propagation of the waves can be understood by studying the propagation of wave fronts. An outward normal drawn at any point on the wave front represents the direction of the wave at that point. In terms of energy, we say that the energy of the wave propagates in a direction perpendicular to the wave front. The speed at which a wave front travels is the speed of the wave. Waves on the surface of water are two-dimensional, and hence the wave fronts are circular in shape. But the waves from a source of sound or a source of light in a homogeneous medium spread in all directions and are three-dimensional in nature. Now consider a point source of light placed in a homogeneous and isotropic medium, emitting light waves in different directions. If the medium is homogeneous, the speed of light waves is the same throughout the medium, and if it is isotropic, it is the same in all directions. The loci of all points which have the same amplitude and vibrate in the same phase forms a sphere with its center at the source of light. Hence, a spherical wave front is generated when a point light source is placed in a homogeneous medium. At a large distance from the source, these spherical wave fronts have large radii of curvatures. A small portion of a spherical wave front at a very large distance from the source can be treated as a plane wave front. In physical optics, we visualize light as waves and wave fronts. In ray optics, we visualize light as rays. A line drawn perpendicular to the wave front in the direction of its propagation is treated as the ray of light in ray optics. Note that a wave front is a surface of constant phase. If a particular wave front is a locus of points with maximum amplitude, it continues to be like that as it propagates through the medium. Christian Huygens proposed a geometrical method known as the Huygens principle for finding the shape and location of a wave front at some instant from the knowledge of the shape and location of the same wave front at an earlier instance. According to Huygens' principle, each point of a wave front is a source of a secondary disturbance and generates spherical secondary wavelets, which spread out in all directions with the speed of the wave in that medium. If a tangential surface common to all these secondary spherical wave fronts is drawn, then it gives the new position of the wave front at a later instant. This surface envelopes all the secondary wavelets. To understand Huygens' principle, let us now consider a primary wave front AB propagating in a homogeneous medium. Then, according to the Huygens' principle, each each point of AB acts as a source of secondary disturbance. The secondary wavelets emanated from these points are spherical in shape and spread in all directions at a speed equal to the speed of the wave. If the speed of the wave is v, then in time t, the radius of the spherical wavelets becomes vt. The tangential surface common to all these spheres in the forward direction gives the shape and location of the new wavefront after t seconds. In the image, the surface a'b' represents the location of the wavefront AB after t seconds. The secondary wavelets must be directed backward as well as forward from the secondary point sources. If this would be correct, we would get a surface such as a'b' as a back wave. But experimental results do not show the presence of any such back wave. In order to explain this, Huygens proposed that the intensity of the spherical wavelets is not uniform in all directions, but is maximum in the forward direction and zero in the backward direction. Hence, the wavelets as well as the whole wave always propagate in the forward direction only. Now let us use Huygens' principle to find the location and shape of a plane wavefront at a later instant of time t. Let AB be a plane wavefront at time t equal to 0. According to Huygens' principle, each point of AB acts as a source of secondary wavelets. The radii of these spheres will be Vt after t seconds. The plane touching these small spheres in the forward direction gives the shape and location of the new wavefront after t seconds.